Hi everyone, welcome to my talk. Today I'm going to talk about our work on quantum-inspired sublinear algorithm for solving low-rank semi-definite programming. This is a joint work with Chia, Han-Xun Lin, and also Chunhao Wang. This is the archive number of our paper. I think our paper is a topic both on quantum and classical side of theoretical computer science. So maybe let me first introduce you some very basic notations of quantum computing. Yeah, so it's like a two-side tutorial. So quantumly, instead of a bit, we have a qubit. So a qubit is basically a two-dimensional vector like this. So basically, we are going to characterize quantum computing throughout the language of linear algebra. So it's basically a two-dimensional vector like this, where a squared plus b squared equals to 1. This is a quantum state, the qubit. And if we measure this qubit with probability alpha squared, we will get the state, the first state usually is the 0 state. And with also, on the other hand, probability beta squared, we will get the 1 state. So this is specifically about the qubit, but on the other hand, we also want to consider some operations. So quantumly, instead of like AND gates, OR gates, in general, we have a quantum gate that we can basically use an arbitrary kind of unitary transformation that basically a unitary transformation will keep the norm, the L2 norm of vectors. So it's basically, as long as a unitary matrix, you can map a corresponding quantum state to another quantum state like this. So this is the thing that I just mentioned is about a one qubit. So in general, you can have multiple qubits like this. So probably you have n qubits, and then this system becomes a vector of dimension 2 to the n. And in general, you can work on this a long vector here. And for instance, you have n qubit here from left to right. They are basically, these are all quantum unitary gates. You can operate them and basically transform from left-hand side to the right-hand side. And this is the final quantum state that will result. So today's talk is basically about how you are going to replace quantum algorithm by classical algorithms. And actually, especially focus more on like the perspective of theoretical machine learning. So we are going to first highlight some recent quantum algorithm for machine learning that can actually achieve polylogarithmic time. So many of these works becomes on the seminal work of Haro, Huston, and Lloyd on solving a sparse matrix inversion problem. And also there are some other subsequent work, for instance, on data fitting, on page rank, etc. And I think there are also more recently you have this kind of work on like discriminant analysis and also the recommendation system result. So today we are going to zoom in a little bit on the recommendation system result, because for recommendation system, it essentially has a low rank structure because you want to recommend something that is only a few kind of things, and typically this is more regarded as a low rank approximation of the corresponding input matrix that is given as the input of the data points. So the quantum algorithm, the polylog time quantum algorithm due to Kernidis and Prakash in 2016 works like this. So if finally you want to get some sample like this, so the input that is required is taken as some quantum state like this. So in particular, the quantum, there is probably something called quantum random access memory, that after having access to such kind of quantum random access memory, you want to get some access to matrix A here, you make it to be a quantum state. And after marrying this quantum state and perform with some interesting quantum algorithms, you can solve the recommendation system problem. So a very seminal result that is actually published in Stock last year due to Evan Tang is that for the specific problem of recommendation system, but it has a low rank structure, you can actually replace the quantum QRAM here, this sample here, by a certain kind of classical sample here. So we don't furthermore have the quantum state here, but we instead have a classical kind of sampling access to the matrix here, and we can finally solve the recommendation system. So essentially, this dequantizes the previous quantum algorithm due to Kernidis and Prakash, and give like a quantum-inspired classical algorithm that with roughly the same complexity performance. So to be more specific, let's zoom in a little bit about the model that Evan Tang actually used. So basically about the classical analog of the model that we want to consider. So you see that like if you have a quantum state and if you want to measure the quantum state, this is really like some kind of sampling-based data structure. And actually here we are going to really consider a classical sampling-based data structure called sampling query access. So specifically, if you have a vector V like this, so the SQ, the acronym for sampling query, is going to be something like this. So if you give me a certain index, I will tell you the index I with probability of Vi squared over the L2 norm of the whole vector V here. So you see that this is exactly the same as marrying the quantum state V here as the output. So we just use this classical data structure to simulate the quantum corresponding data structure. There are also some other requirements for the SQ query access. So for the query, it's just like the input is I, you can directly tell me the VI without, this is really like a query instead of the sample for the first part. And after having that, we require some further information. For instance, we require that we know the norm of the matrix of the vector V here. They can tell me the L2 norm of the vector V here. And for instance, just like we have such kind of notations of the QV here. And in general, this is about, although this is about a vector, in general, you can think about the sampling query access to even matrix A here defined in a similar sense. So you can just look at each row of the matrix A here as the corresponding sampling query access. So in this work, we basically consider such kind of sampling query access, and we want to apply such kind of sampling query access to solve semi-definite programs. So semi-definite program has been a central topic both in classical and quantum theoretic computer science. And in particular, today we talk about such kind of problem. So the problem is that we want to maximize the trace of a certain a trace of C times X, where the C is a target matrix that is given to you. And also we have a bunch of M subjections such that the traces of each given matrix AI times X is bounded by some upper bound small AI. And also very importantly, because this is a semi-definite program, we require the variable matrix X here to be a positive semi-definite matrix. That is to say X is symmetric and all its eigenvalues is non-negative. So here, as a normalization constraint, we require all the matrices AI to C, and also the matrix C here to have spectral norm at most 1. So it's basically a normalization constraint. So previously, this is a very important topic in the study of quantum TCS, and actually previously quantum literature has discovered that actually we can achieve some polynomial speed up compared to the best known classical algorithms. So for instance, previously quantum algorithm can reach to the cost of square root of m plus square root of n, where m is the number of constraints and n is the dimension. So classically for both parameters, the cost is at least linear. So that is the reason why this is called like a polynomial quantum speed up. And furthermore, there is a work showing that even for low rank cases where the constraint matrix AI, and also the target matrix C has rank at most R, actually quantum algorithm can achieve polylogarithmic interdimension dependence. That is basically to say we can still keep the square root of m complexity dependence on the number of constraints. But on the other hand, the polynomial can be all jumped into a polynomial R instead, and also the polynomial dependence in n goes away and actually becomes a polylog dependence. So this is a very interesting result, and a very natural question here to ask is, can we actually get quantum-inspired classical algorithm for solving SDPs? The main result of our work for this MFCS is that we give a classical algorithm that achieves the same complexity. Although the polynomial degree here heighted is a little bit higher than a quantum counterpart, but you see like basically they enjoy the same form. So we basically achieve the same the same complexity, but without quantum, we only use the classical sampling query access. So on the other hand, it's basically to say that although like the previous quantum SCP solver result, it is very interesting that we can reach the polylog dependence, but actually it only means polynomial speed up compared to the classical counterpart, because the same phenomenon can also be achieved classically. So this is our main result that we achieved. And also we found one application back to quantum computing. So in quantum computing, there are very important tasks is to learn quantum state. And in particular, if you want to learn state based on measurements, this is typically called shadow tomography. So mathematically speaking, the goal is just to approximate the trace of your state times a certain measurement operator EI within some error epsilon. So each operator, quantumly, if we call it a measurement operator, and I think the term is called the two outcome POVM, it is just like a positive semi-definite matrix that is between 0 and the identity. So smaller than identity just means all the eigenvalues of EI is smaller than 1. So we basically show the same phenomenon for the shadow tomography, that the problem can also be solved with the same cost, which is only polylogarithmic dimension dependence, but a poly dependence in the rank R. Okay, let's very quickly go through the technical contributions of our work. So this is really like a long line of research about classical like a randomized linear algebra techniques, but we further make quite non-trivial developments. So a first lemma that we want to look at that based on this sampling query access is that if you have access to, maybe if you want to estimate the multiplication of V dagger times A times W. So, and also on the other hand, you are given the sampling query access to these two vectors and also the matrix A here. You can actually give a good access of this product with the additive error epsilon and with high probability only using this time. So you see that this bound is actually independent of the dimension dependence, but only has like the norm dependence, like the spectral norm, the Frobenius norm of the matrix, etc. And actually, this is very good. So how does actually people achieve this? If you just like have this kind of vector V, A, and matrix A, and also the vector W here, you consider some random sampling based on this SQ query access. So basically, for instance, if you have a large matrix A here, you can push the button. It's just like you push the sampling button of the corresponding oracle. Then maybe you sample only a few rows of the matrix A here. And after having this kind of samples, furthermore you make like column sample. This is the row samples, and you can further make some column samples. And finally, the resulting matrix is just the intersection of all the rows and the columns that you sampled from. So there are many non-trivial things that you can actually play on this small matrix that you sampled. Actually, this really originated from the old work due to Fritz, Kahn, and Van Pella. That the good thing is that you can actually apply approximate version of the singular value transformation for such kind of problem. So for instance, if you decompose the matrix M here to having such kind of form, this is basically the standard singular value transformation. On the other hand, this is really like a large matrix that you want to make a corresponding singular value transformation. So what do you do? So this S dagger is just the S that we actually resolved in this in the middle step, which is this very long but very thin matrix here. You can actually approximate the singular value transformation, the singular value decomposition for the original matrix by just making an SVD for the small matrix W here and actually approximate the singular vector of the original large matrix A by this kind of very thin small matrix VI here. And actually, there's a good approximation. Actually, each of them we are going to give the corresponding statistical SQ query access for them. And actually, if we define the N by P matrix V to be something like this, and also with we have this SQ access, then actually the FKV can show that in this kind of things, the matrix A here compared to this really like approximate version of the singular value decomposition, you can actually see this is a very good approximation for the original large matrix A, but you really saved a lot because the singular value transformation for the small matrix W is much cheaper than that of the original large matrix A. Yeah, so one of our important contribution here is that we can actually extend the result due to Fritz, Kahn, and Van Pella, and actually we can do something more than once. That, for instance, we can give a better analysis here that not only works for a specific matrix A here, but in general, especially for the goal of solving the semi-definite program, we need to do the similar singular value decomposition for a summation of some matrices. And actually, this is highly non-trivial. And actually, this is the technique that actually we call the weighted sampling. So why do I say that this is highly non-trivial? So maybe we just think about this example. So the naive way, for instance, if one matrix, the A1 here, you have all one row, and maybe for the matrix A2 here, you have all minus one row. If you just plus them together, actually, I think from the value point of view, they are all going to be zero. But actually, if you consider corresponding SQ, directly consider SQ query access, you will actually get this row, and you actually get this row. But for the summation, if you directly consider SQ query access, this row won't be sampled. So this is something you're probably going to be fixed. And actually, this is our technique called the weighted sampling. So how do we achieve this? We just assign weight of each matrix correspond to the norm of the row that we are trying to sample. And actually, you see that after the summation, this norm is going to be zero. And actually, this actually perfectly solves the problem. So another technique that actually we consider is called a symmetric approximation. So in particular, how you are going to compute like the statistical query access of the function of such kind of like the matrix A1 to A tau after giving their corresponding SQ query access. So by the FKV paper, the Fritz, Kahn, and Van Pella, we just mentioned that A can be approximated by A times V dagger, so which is basically the right-hand side of the approximate singular value transformation. And also for the right-hand side, we have such kind of A here. So multiplying them together, we can see that A approximately equals to U times U dagger times A times U V dagger. So furthermore, we can actually take a closer look at such kind of matrix multiplication structure. You see that the A here is a very large matrix, but the U here and the V here are going to be some tall but thin matrix here. We have the corresponding SQ curve access to the matrices U dagger A and also V. And actually the goal here, we are actually, because we have this kind of gadget that we propose for multiplying the vector matrix vector, this kind of U transpose times A times V. And actually this is because you know like the side length of the thin part of the matrix U dagger and V. So this is basically P, and this is also basically P. So we are just going to estimate, we're just going to take each row of the matrix U dagger and each column of the matrix V here. And actually we are going to apply our gadget U dagger times A times V for P squared times. And actually, after having this kind of small matrix here, we are furthermore going to compute matrix function on this small matrix U times dagger times A times V, and also a corresponding entry can be computed easily. So for our goal of semi-definite programming, actually this everything is symmetric because we basically play with Hermitian matrices. So speaking of the singular value decomposition, actually it reduces to eigenvalue decomposition. Actually, in our case, we actually apply, in our case that we apply, we always have U equals to V because it is eigen decomposition. But this is just a proof of principle thing. And actually, in general, this elateral can be generalized to something called asymmetric approximation. There, it's just like if the matrix A is not Hermitian matrix and B not equals to U, the same discussion still works. But it's basically originated from our work that in our work, we both have the technique of weighted sampling, but also this technique of symmetric approximation that really further motivates a future study. I will briefly discuss about this at the end of my talk. Okay, so I think this is really the introduction to my techniques, and I think for now I should probably also give you, it's basically give you the idea of about how our quantum algorithm works. So our quantum algorithm follows a specific kind of algorithm framework called the matrix multiplicative weight framework due to Aurora, Haza, and Kali. So what is the idea of solving the corresponding semi-definite program? So we just make some guess initially. So for instance, initially we just guess this to be the normalized version of the identity matrix. So of course, this can be something bad. Maybe, for instance, you will naturally find a constraint matrix AJ that is not satisfied. So for instance, let's just call an AJ that is well likely to be something like the trace of the AJ times rho to be larger than this requirement. You know that it is required to be smaller than AJ, but we have a threshold here that is even larger than AJ plus some epsilon. So what encounters, if you encounter this, what is the solution here? It means that the gas is not really good, and this specific constraint AJ is specifically not something you are really in favor of. So you are really going to make a renormalization. So you are going to renormalize the corresponding matrix AJ by a different weight. And actually, each time you are going to find a well-weighted constraint, you mark them down, and actually you are going to correspondingly prepare a new matrix like this, a new state like this, which is going to be a normalized version of the exponential of the summation of all the previous well-weighted constraints. So you are going to do this again and again. So basically, as long as the row here is not currently satisfied, that is to say, at least one of the current constraints is not satisfied, then basically you are not satisfied in the semi-definite program. You are going to do this, and I think you are going to call the iteration for, roughly speaking, like 16 times log or epsilon squared times. And actually, you can prove that such kind of structure, which is the matrix multiplicative weight framework, can promise that if you always find a valid constraint, it just means that the system is not feasible. But on the other hand, you can find a solution that is very good. One thing that I forgot to mention is that, so this is basically like a feasibility testing problem that you test whether a certain matrix is feasible in the current SDP or not. But in general, recall that the SDP, we have this target matrix, a trace of C times X. You can also actually regard this as another constraint if you consider binary search on the SDP value. So for instance, if we want to make sure that whether the solution of the SDP is larger than, say, 0.1 or not, you can just assume there is another constraint about like the trace of C times X is smaller than 0.1 or not. And actually this, you can just regard this as another constraint and regard this problem as a feasibility problem. So this is basically about the MMW is a framework that you can directly solve the feasibility testing problem of the SDP. Okay, so this is the framework, and actually the Aurora Hasan-Kali paper is a classical paper for Sony SDPs. But the problem is that each step is quite costly. So it's basically this step is about the matrix exponentiation, and actually in general the cost is at least to the exponent of matrix multiplication. And I think in general this is not very good. But later on there are quantum algorithms that study specifically about this step, and also the testing of trace step in general, like matrix multiplication, is expensive classically, and you want to give a better algorithm. So previously, quantum algorithms really take a closer look at these two steps, and actually they have a fast quantum algorithm for computing them. So in our work, we basically follow the same pattern and also apply the previous two techniques, the weighted sampling and symmetric approximation into these two parts. But actually, we can give a dequantization of the previous quantum algorithm, and basically assuming the low rankness of all the constraint matrices AJ here, we can prove that these two steps can be solved in polylogarithmic time classically using the SQ query access to all the constraint matrices AJ here based on our techniques. And this is a this is a polylogarithmic time in terms of n, but you got to pay a polynomial dependency, the rank dependence. So this rank dependence basically comes from this low rank assumption is very important, and you see that this is basically going to apply throughout the singular value decomposition. In our case, it's basically eigen decomposition. So if the rank is at most R here, there are only at most R non-trivial eigenvalues, and this is the reason why everything can be significantly simplified. Okay, so I think this is close to the end of my talk, and actually let me make a conclusion here. So as a summary, our main contribution is that we actually dequantize previously quantum SDP solvers to run in polylogarithmic time classically, given a statistical query access. And also as an application, our our quantum inspired classical SDP solver can be used to learn quantum state using measurements and to solve this specific problem of shadow tomography. So we actually, in our work, we gave two techniques, the weighted sampling and also the symmetric approximation that actually can not only solve our SDP work, but later on motivate some interesting work. And actually the authors of this MFCS paper, and together with the other two people, Andrew Shagibian and Evan Tang, and actually we gave a very general framework for dequantizing quantum machine learning papers. So basically the papers that I listed at the very beginning of my talk, so they can basically be dequantized. And actually this has been, a paper has been accepted by the stock this year. So let me also very briefly highlight the open questions that we are currently having. So a very important open question is that can we give fast sampling-based algorithm for Sony LPs? So this is in general about Sony SDPs and basically about the rank of the problem. But in general, for LP, you not necessarily have a low rank assumption, but LP is also a great simplification of the SDPs. And maybe you also want to explore fast sampling-based algorithm for LPs because of the importance of LP in practice. So another very natural question is that what is the empirical performance of our sampling-based methods? So there are some testing results on the other sampling-based methods. So in particular, there are currently existing numerical experiments on Evan Tang's dequantization algorithm for recommendation systems. And we also very look forward to test the empirical performance of our sampling-based method and see if actually they work better than like the recent classical algorithms in practice. Okay, so this is basically the end of my talk, and I really want to thank you for your attention here.